Now it's time to start discussing the issue of energy and power in a transverse wave. And this holds true for longitudinal waves as well, but the simplest case is a simple sinusoidal transverse wave. So if we have a wave traveling to the right, um, consider a small mass element delta m. Okay, then the kinetic energy of that little element, the differential amount, or I should say, the difference amount of kinetic energy for that tiny piece of mass, is 1/2 times that amount of mass times the velocity of the wave squared. Okay. Um, and remember, so this particular piece of mass is only going to be oscillating up and down. Okay? So the velocity of the wave is not necessarily the same. This velocity of the wave is not necessarily the same as Vy. Okay? So that's one thing to note. Remember that Vy is going to be given by negative a. Well, let's start back at the beginning, right? Why not? So remember that y is a times sine of k. Well, in this case, to be kx minus omega t. All right. And so if I differentiate this, this gives me Vy, and this is going to be a cosine kx minus omega t times minus omega, which is going to give me negative a omega cosine kx minus omega t. And so the VW, or the velocity of the wave, is equal to omega over k, but the velocity in the y direction is going to be sinusoidal. Okay, so that's the first thing to note. Another thing to note as we work through this derivation is remember that the delta m, the mass of this little differential piece of mass, is going to be equal to the mass per unit length, mu, times this length dx. Okay? So, I really should say delta x. So delta k is going to be 1/2 times mu times delta x times Vy squared. And if we let in the limit that delta x goes to 0, this becomes a differential, not just a delta. Okay? And well, I'm being sloppy mathematically. This is still delta, and then when we apply the limit, this becomes your differential. Okay. And so now we have an expression that we can integrate, right? So what we're going to do is we're going to look at one wavelength of the wave, and we're going to integrate this expression over that wavelength to get the energy, the total kinetic energy in that segment of the wave. All right. And we're going to do this. We're going to let t equals 0 for simplicity, but this is okay because every piece of the wave, well, let me put it this way. When t equals 0, the rope is in this shape. But any time later, there will still be a symmetry, even if it's not exactly in this part of the sinusoid cycle. It will still be one complete wavelength of the sinusoid cycle, and therefore the kinetic energy total over that wavelength is not going to change. Even if the kinetic energy of each individual mass piece changes sinusoidally, their total sum is not going to change. So that's the argument that this is going to rest on. Okay, so then we can say that the kinetic energy over a segment of wavelength is going to be equal to the integral from 0 to lambda of 1/2 mu Vy squared dx. Okay, and a couple of things happen. So if we let t equal 0, then Vy is equal to negative a omega sine kx. All right. And so this is what we're going to plug in for Vy, but we're going to square it, right? So with that in mind, this becomes from 0 to lambda 1/2 mu times a squared omega squared. Whoops, this is cosine. Cosine squared kx dx. And a lot of stuff comes out because it's constant, so we have 1/2 mu a squared omega squared integral cosine squared kx dx. And the punchline is that this integral, let me redraw that. This integral goes to 1/2 lambda. The argument for that is, well, first of all, you can prove it to yourself by using, an integral calculator, or an online calculator like Wolfram or Integral Calculator or something like that. But the reason is because sine and cosine, when I square them, equals 1, and they both contribute half of it. Okay, so this becomes 1/2, and when I evaluate that from 0 to lambda, it becomes 1/2 lambda. So the result is 1/2 mu a squared omega squared times 1/2 lambda, and that equals 1/4 mu a squared omega squared times lambda. And you can go through the same process, okay, for the potential energy, all right? But the bottom line is that the potential energy over the same wavelength gives you the same result. Oop, it's 1/4. The total is 1/2. Okay, so your total energy over one wavelength is going to be equal to your kinetic over that wavelength plus your potential over that wavelength, which is going to be 1/2 mu times a squared omega squared times lambda. Now, so here's the intriguing part. Okay, so the power is the rate at which your energy is used. So this is delta E over delta T. Okay. This needs to be lowercase. We're not ready to put in the total period yet. So if I think of this, all right, let's come back to our rope here. Over one period in time, the rope will come back to this shape, right? The rope will come back to this identical shape one period later, and it will have this total amount of kinetic energy associated with it, and it will have this amount of total potential energy associated with it. So over that cycle, it will have this amount of total energy associated with it. So we can say that E over one wavelength divided by the period of the wave is equal to delta E over delta T. And plugging this in, this is 1/4 mu a squared omega squared lambda over the period. But lambda over the period is the speed of the wave. So this is VW. Okay? So 1/4 mass per unit length times the amplitude squared times the angular frequency squared times the velocity of the wave is the power that is dissipated by this rope. As in this particular case, it's a rope. It doesn't have to be a rope. It can be any mechanical wave. But this is the power associated with that wave, right? So this is the amount of energy per unit time that the wave is going to use, okay? So with that in mind, the next set of lectures will be based on interference and waves on strings, okay? So think of things like guitar strings and piano strings, all right? And we will see you then.